Since we dealt with the alkenes last time, we can now deal with the alkynes, where we have a triple bond in between two carbons. In a lot of cases, this is going to behave like that old song of anything you can do, I can do better, only it's going to behave towards an alkene as anything you can do once, I can do twice. And the reason for that is that we have two pi bonds instead of just one. So what we did with alkenes, generally speaking, is going to happen twice with alkynes. That's a good guess. There are some cases where we can control that and stop it at one, some cases where we can't. The reason that we use alkynes most commonly is that they're relatively easy to put in place. That is not the case for alkenes. That is not the case for a lot of other groups. It has to do with the fact that the triple bond causes some changes in the carbon to hydrogen bonds of an alkyne, if we have those. This is a specific example. This is acetylene, the simplest possible alkyne. This is the stuff that's used as welding torch fuel, among other things. So you can kind of guess that it's probably a little on the energetic side. The useful part here is that, as I was beginning to say, those hydrogens are suddenly accessible to us. When it comes to alkanes, we really can't do much there. So if we have methane, that pKa is pushing 60. For all practical purposes, you're not getting that off with a base. That's about as unacidic as it gets. So we can't really do it. I mean, there are some that will do it, but obviously you can't have much else around because anything that will take that off is pretty much going to tear anything else to shreds. When we're looking at alkenes, the situation is not a whole lot better. We're still looking at pKa's in the 40s, usually around 45 for a simple alkene. Again, are there bases that can do this? Yes. Would you want to use them in regular use? Absolutely not. So, not exactly ideal. But by the time we get to acetylene, now, because of the change in hybridization, now we're down to a place we can actually work. We have a lot of bases that can actually take off a pKa that's around that number. In fact, it's not all that hard to do. And therein lies the key to being able to use acetylenes as precursor functional groups, that they're relatively easy to put in place because if we start with the hydrogen on the alkyne, we can substitute that with a lot of other things, but probably most importantly for us is a carbon. Now, that's going to look awfully familiar because we've done it before. So, I have something like this. We're just going to say base minus for the moment. We're not worried about what it is for the instant. That's going to give us this, an acetylide anion, where I have a negative charge now on a triply bonded carbon. The useful point here is that I can actually treat this with something like an alkyl halide, so I'm just going to use a simple one like, bromoethane or something, and I get something I told you was going to come back and haunt us over and over and over again. I get an SN2 reaction. So the consequences of that is I form a new bond to the carbon. Up until now, I haven't been able to do that. We really couldn't easily do that with the alkenes. There are exceptions, of course, but they're not nearly as simple as this. And this is controllable where I can selectively do it again if I started from acetylene like I have here, and then actually get something else. So let's just say I use a methyl group this time. So if I did the same thing, base followed by this time a different alkyl halide, I would get a different carbon on the other side. The point of all of this is that if I can put an alkene in place, as we're going to talk about later in this lecture, if I can put an alkyne in place, as we're going to talk about later in this lecture, it means that I can actually transform that into an alkene, I can transform it into an alkane, I can transform it into ketones, sometimes aldehydes. I can transform it to carboxylic acids. So I have a wide variety of functional groups that I can get my hands on if I can put an alkyne in place. So it helps that this reaction is actually very simple. It's a deprotonation of a relatively acidic hydrogen and then an SN2 reaction, which we know works well. We spent a whole lot of time talking about that one, and I warned you it would come back in pretty much every chapter. Well, here it is. This isn't the only example in this chapter, but it's a really important one. Okay, so in terms of bases, we need something that is going to be slightly Our base choice is a little bit limited, but it's not terrible. We have a couple of things we can use and get away with, some of which we've dealt with before, some of which we haven't, but needless to say, they're going to be a lot stronger than something like sodium hydroxide. The common ones we're going to see here, things like butyllithium, so where I have an alkane with an anionic charge on it. You can use LDA for this if you wanted to. I think that's the one your book talks about, which is a diisopropyl, two isopropyl groups on a nitrogen with an anionic charge on it. The point is we just need something that's strongly anionic to rip off a hydrogen. The different part here is that when we use a really strong base, we cannot be doing this in the typical SN2 solvents that we talked about before. DMSO, DMF, acetone, those things would not be good here because once that, assuming the base left the solvent alone, the nucleophile would then attack the solvent and we wouldn't get the product we want out of this. So we have to choose our bases relatively carefully. That's not entirely that hard to do, but generally speaking, LDA is a good one because you can just basically buy it or you can make it from butyllithium and diisopropylamine, either way. And it's relatively simple to use, despite the fact that it's a considerably stronger base than what we would normally deal with. Okay, so we can do that. Let's talk about some of the other things we can do in the context of what we did in the alkene chapter. And that is, we're going to look at some of the reactions that we have in common with the alkenes. I'm going to make this unsymmetrical because I want to do it as a compare and contrast. So I'm going to use an unsymmetrical alkene that we talked about a lot last time, and a similarly unsymmetrical alkyne so we can see regiochemistry again. Never forget the cation rules. Hyperconjugation brings more stability, even if we're talking about something that is not strictly sp2 as a cation. If we go through a cation here, it's going to be sp because it was already sp. And remember, breaking that pi bond to form a cation did not change the hybridization for the alkene. Well, it's not going to change it for the alkyne either. So for things like HBr, we ended up with a cation here, and then eventually the bromine on the more substituted of the two carbons. Surprise, surprise, when we do HBr with the alkyne, we're going to see exactly the same thing happen. Now, some books will suggest that you can stop this halfway. I don't have experience trying to do that, so I won't contradict them, but it seems difficult to me. So what we're going to have at first is this. Where we've gone through an attack similar to before, the pi bond attacking the hydrogen, causing it to ditch the bromine. That gives us now a hybridization on one side that's changed. Here, these were both sp2 for the alkene. Afterwards, the cation is still sp2, but where the hydrogen added is now sp3. The cationic one has not changed because empty orbitals do not participate in hybridization. The exact same thing for the alkyne. The one on the left was sp hybridized, as was the one on the right. after the first addition, we're now looking at something that is sp2 hybridized versus a cation that is now still sp. So the next point is going to be the bromide attack, just like it was for the alkene. This is a linear cation, so just like a flat cation from the pi bond above, there is no preference as to which side it would attack. Not that it would matter in this case, but in case I had labeled the hydrogen where I could tell which side it ended up on, I would end up with a mixture of cis and trans alkenes. In this case, it already had a hydrogen, so I can't tell. But most likely, this is not going to stop, and it's going to undergo this again. But the same rules apply. Now I'm looking at an alkene. We know that reacts with HBr. We know how it reacts with HBr. We know where the bromine ends up. So what we're going to end up with is this. We're going to end up with now a dihalide. We're going to end up with a dihalide. Now, at first, that doesn't seem overly useful, but there are some significant uses for putting two halogens in like that. And as I said, there are some cases where you may be able to stop this halfway through. I have never done that, so I don't have an opinion there. But for my purposes, the way this is normally labeled so that we're clear is that we use excess reagent. We use excess HBr, which means there's more there than is needed to do one reaction. There's more there than needed to do two reactions. Here's one of the little labels that we use. It is unfortunately a little confusing if English is not your first language, because it is a phonetic version of excess. Excess means more than you need. What some people will write is the phonetic letter X and letter S to represent excess. I've had people ask me all kind of things about that over the years, like, what does that mean? Crosses? No. What's X's mean? It's XS. Spell it out and you'll understand why it's there. It just means people are too lazy to write out the word excess. It's not like it's hard to spell, but in case you see this, I want you to know what it means, because it's very likely that it appears at different places in your textbook, as well as references you might see online. All right, so this is one where there's not going to be any regiochemistry. Well, there is regiochemistry. We're still looking at more substituted carbon getting the more anionic of the two incoming groups, because it is the better cation, both from the alkyne in the first addition and the alkene in the second. It's still the better cation, but there is no stereochemical issue here because we're not actually able to stop this halfway through. And that's going to be the case. We don't have rings really with alkynes in them. There are some exceptions, but they're very large, and we don't need to dwell on that right now. So we don't have that type of loaded example that we can use to demonstrate the mechanism of addition quite as easily as we did for the alkenes. But what we do have is the ability to stop some reactions along the way. The most famous of those is how we get to an alkene from the alkyne. But first, let's look at the alkene version, getting to an alkane. If we treat an alkene with hydrogen gas and a palladium catalyst, usually palladium metal suspended on carbon, we get hydrogens added on the same face of what was the alkene. Here it doesn't matter because we're not dealing with a cyclic case. Well, if we do that with an alkyne, we're going to see exactly the same thing. I'm going to go with a symmetrical alkyne now so we can at least look at it along the way. There's going to be a reason for that in a moment, you'll understand. But if I just use the same conditions, what I end up with is an alkane. I end up destroying not one but both of the pi bonds and replacing all of those with hydrogens. So I end up with 4 new hydrogens, 2 on each of what were the alkyne carbons. That's okay, but that doesn't give me another functional group. The alkane, to my mind, is not really a functional group because aside from radical halogenation and combustion, it really doesn't do a whole lot. So I can't really convert that to something that I can work with more later. I find that a little frustrating. I mentioned that you could use an alkene, that you could get to an alkene from an alkyne. It involves a similar version of this reaction, but taking it down a notch. Now, what I want to do is take that hydrogen and palladium example and give it a bit of a chill pill. I want it to slow down and not go twice. I want it to hit the alkyne. I do not want it to react with an alkene. What we're not seeing here is along the way from the alkyne to the alkane is the alkene, but it's not around, so we really can't catch it. It's just as reactive under these conditions, so we don't ever see it. We'd like to be able to stop things there. It would give us access to alkenes. So we need to calm this down a little bit. Not really any way I can calm down hydrogen gas. It is what it is. But the catalyst has a role in breaking the H to H bond, and it's a bit esoteric for us to go into here, but one thing I can do, in this case the catalyst plays the role of sort of like Three Stooges, where it grabs onto both pieces to a certain extent and slams them together. So it's actually holding on to the hydrogens, and at certain points it will grasp onto the alkyne or the alkene and then smack them together like the Three Stooges bouncing each other's heads together. So we need to basically be able to control that a little bit if we're going to give this any type of selectivity. That's the trick, and it does actually work, but it requires a lot of work. It requires additional chemicals. We have to basically take that palladium and, to use sort of unpleasant television terminology, we have to kind of kneecap it a little bit. We have to hobble it, make sure it doesn't actually get too uppity anymore. We take it down a notch, beat it up a bit. What we do, actually, is called the Lindlar's catalyst. What it is poisoned palladium. And that term is used with the understanding that it basically is a, horror movie type term. What does it mean to poison something? It means to give them something that's toxic. Well, we're not really going to kill the palladium, but we want to make it really sick and slow. So instead of just palladium or palladium on carbon, what we get is palladium. We get usually something like barium sulfate, and we usually get an aromatic thing that's a base called quinoline. And that takes up some of the binding sites on the palladium and changes its electronics a little bit so that it can still do one job, but it's a little too blocked out to do that second reaction. So if I take the same alkyne and I treat this not with palladium, but with this mixture of stuff that's called Lindlar's, what I get is just what I saw with the alkene, which is the syn addition of hydrogen, and it stops. So what I get is that intermediate that I could never see before in the regular hydrogen palladium additions as my final product. Two hydrogens on the same side, the end. It stops. It is not going any further for any reason. Now, having spent almost a semester now dealing with an organic chemist, you should know that sometimes we are similar to petulant children, in that if we're given one thing, we will always find a reason to want the other. Like a 5-year-old at Christmas, but I wanted that toy, I wanted this toy, I wanted that toy. They're never happy. Well, neither are we. So in this case, we've got a reaction that gives us syn addition, that gives us a cis or a Z alkene. Well, what if we want the other one? It's not going to happen this way. But that does not mean it's not going to happen at all. The reaction that will accomplish this is called a dissolving metal reduction. Now, What that means is that over the course of the reaction, it looks like the metal dissolves. It does no such thing. It reacts. Metals don't dissolve. They react. But reacting metal reduction doesn't sound as cool because pretty much it tells you what's going on. So why you wouldn't want to say that, I don't know. I will preface this by saying it is the only example that we use commonly in either course that involves both, keyword, both radical reactions and polar steps within the overall mechanism. It is the only example where we do that. It is a little bit on the weird side. We're starting with something symmetrical, so we don't have to worry about preferences. But the point is that we're going through both types of problems here at different times. And that makes this a little bit weird. We're using sodium metal. We're using liquid ammonia. This is not ammonium hydroxide. This is gaseous ammonia that has been liquefied. It does not have the large quantities of water in it, which would present an obvious problem with sodium, unless you happen to like things blowing up in your face, at which point order it and ship it to your house. Don't bring it here. Okay, so what happens first? Well, we have sodium. Sodium in its metallic state, and one of the reasons it's so reactive, is it has an unpaired electron. This is the 3s1 electron. It's all that there is. This is group 1 element, not an ion. That means it has one electron in its outer shell. It's just sitting there. That's why the alkali metals are as reactive as they are. So what we have is a pairing up of that. The alkyne is going to take it away. Why does that do us any good? Well, it gets us the sodium in a far more stable state. It gets a sodium cation now. Its electron that it had in the outer shell is gone. It now has a noble gas configuration. You should be having thoughts of General Chemistry 1 right about now. In the meantime, we have now only 2 bonds in between the 2 carbons in the center of what was the alkyne. One of them is a radical, a single unpaired electron, the one on the left. The other of them is an anion, because it had one electron from the alkyne split. It also took 1 electron from the sodium. That's our ionic state. That, a carbon with a lone pair of electrons, is an anion. Now, I'm not trying to draw the hybridization correctly. Technically, the lone paired, the carbon on the right is sp2. The one on the left is debatable, but most likely it's sp2 as well. Now, we have ammonia. Compared to that, ammonia is a wonderful acid. So the ammonia will get deprotonated. Now, we're going to have one of our hydrogens in place, and let's go ahead and draw this properly, the hybridization properly for the radical that remains. It is now sp2, so it was sp2 all along. I just didn't draw it that way because I wanted it to be clear where the electrons came from, where they went, without rearranging the geometry. Now we have a second round where another sodium gets involved, giving up its electron. Now we're not going to have to break a pi bond to get a radical to work with. There's already one there. So now we're going to have the anion on the left of the 2 alkyne, of what were the alkyne carbons, and yet another sodium cation laying around. So that when we're done, now we have another ammonia. This is a polar step, and what we end up with is this. We end up with addition of hydrogen, trans, anti, on opposite. So the alkene that I end up with is now trans or E. The two hydrogens are on opposite faces of what are opposite sides of the remaining alkene, and the reaction stops here. The byproducts, sodium metal as a cation, a deprotonated ammonia as an anion, so this is sodium amide, or sometimes just called sodamide. It's actually a reasonably good base, but we don't have anything reasonably acidic around left for it to chew on. So we don't have a problem with it doing anything else. Afterwards, we'd have to be a little careful dealing with it, but that's true in any reaction you use sodium with in the first place. But the point is, it gives us the answer to the childhood, oh, I want the other one. Okay, then you change the conditions, and it will actually give you the other stereochemical possibility. Hydrogen addition with palladium that's been poisoned gives you syn addition. Doing it via dissolving metal reduction gives you anti-addition every time. All right.